Hello there, welcome to Special Maths Academy. My name is Honor Pius, and today in this video we'll be looking at IMO 2022 problem 3. So this is the third problem in the first day. It goes as follows: let k be a positive integer and s a finite set of odd prime numbers. Okay, so we'll be dealing with odd prime numbers, just keep this in mind. Prove that there is at most one way up to rotation or reflection to place elements of s around the circle such that the product of any two neighbors is of the form x squared plus x plus k for some positive integer x. So this is also something else to keep in mind. Now before going into this, we see that we have to prove that there is at most one way. So this means that there could be actually no way of doing this, or just one way of doing this. If there is no way, then there's nothing to prove. So generally we'll be assuming that there's at least one way of doing it, as of arranging the elements of s in a circle that satisfies this property. And then we want to show that there's actually no other way of rearranging that, meaning that we actually want to show uniqueness. So the focus of this is going to be on uniqueness rather than existence. So for what follows, we're going to assume there's actually already at least one arrangement of primes in this. And now we have two variables as k and s. So we're going to actually just fix k, and then we're going to, for the same k, we're going to experiment on the s that are going to work. So some sets it's possible to make an arrangement, some sets it's not possible. So whatever s we're dealing with, we are already assuming we can form a circle. So by circle we mean placing the primes in the circle in this form. For example, p1, p2 up to pn, where n is the cardinality of s. So we assume that there are s elements, n elements in s. Of course, they are all odd primes. Now, what does it mean for this to be a circle? When we say this is a circle, it means that it really satisfies properties between neighboring points. Okay, so this is very crucial. We'll be using this repeatedly, so just keep this in mind. And so, for example, p1, p2, they are neighbors. p2, p3, neighbors, and so on. And of course, pn and p1 are also neighbors. So we can actually just start this from 1 up to n. In this case, pn plus 1 will just be the next prime after pn, as p1, and pn plus 2, for instance, will be the next prime after that, p2, and so on. So this is like working in mode n, sort of. So that's why this is a circle. And also, it doesn't really matter which prime we start as p1, so long as we fix the starting position and the direction we want to place the elements, then there should be a unique way to do this. Okay, also another thing to just keep in mind is if we have two expressions, then we see that by subtracting, taking everything to one side and factorizing, that once we deal with positive integers, this expression here was going to be positive, so that forces x to be equal to y. So this means that for each pi and pi plus 1, there's a unique xi that actually makes it work, right? And this is what we're going to call the connection between pi and pi plus 1. So in fact, we're going to picture the circle as this, that we have these, which are the primes, so p1, p2, p3, and so forth, and so on and so forth. And then we have strings that actually connects p1, p2, and every adjacent bit. So the connection is just going to be that unique value of x. So for instance, this here we have an x1, so there's a connection here, and x2. So for this to really be a complete circle, we're not just looking at the primes, but also the connections between the primes. So they have to always be that connection. So this will be xn, and those connections are unique once we have the pair of primes we're dealing with. Okay, so we're just going to look at a quick example. Now to make this video as short as possible, I've already prepared the notes, so we're just going to go quickly through them. Alright, so when k is equal to 35, for instance, we have this lineup of primes. So these are the primes themselves, the ones with the bits. The other numbers are their connections, so they are the values of x that works for them. So you can quickly check this. So here is the strategy we want to work on. So the idea here is that we're going to start with a string or a circle, right? And then we're going to kind of deconstruct it into smaller bits, and then show that we can actually build it back to the bigger one, put things back together in a unique way. So for example, by breaking it down, we mean that we could, let's say, remove 31 for instance. So if we remove 31 from this circle, we're going to be left with 7, 13, 29, 5, 11. Right? So actually for this 7 and 13 we already have a connection 7. For this we already had connection 18, connection 10, 4. So the question is, can we actually connect 7 and 11 for instance? So we want to know when we can do this, and then once it's possible to do this, when can we actually try to create 31 back again? Like, how can we be sure we can create some sort of 31 that's going to work for this? So this is going to be the central idea for what we will be dealing with. And throughout this, when we refer to pi, the neighbors of pi will be pi minus 1 and pi plus 1 in a specific circle, and then their connections will be xi and xi minus 1 respectively. Okay, so first of all, we're going to assume n is greater than or equal to 3, otherwise it's not going to be interesting, and also to avoid some mixed confusions. So we'll look at a series of lemmas that's going to kind of build the way for us to get the desired result. So the first lemma is just a very handy one that we use to prove our subsequent lemmas. So if we have a pi greater than the two neighbors, right, then we have this result. So this is going to be very important. We're always referring to this. So the proof of this is that we have pi is greater than pi minus 1, so we have this inequality. And then from the connection between pi minus 1 and pi is greater than xi minus 1 all squared, and then we can take square roots and we get these two nice inequalities. Okay, so more specifically we get these two expressions. Okay, and then if we subtract the connections between these two, we can factorize pi out to get this, and then we subtract their corresponding expressions for x, which is factorizable from what we already did with x and y up here. So we'll always do that, and we get this nice factorization. Now you know this is not going to be 0 because we have pi minus 1 is not pi plus 1, since we have at least 3 primes. So once we arrange pi plus 1, pi minus 1, if we get that pi plus 1 is equal to pi minus 1, that will just complete the second. We have only 2 primes. Okay, so since we have at least 3 primes, this is not 0, meaning that xi minus 1 is not xi, so it's not 0. Also, xi minus 1 minus xi lies strictly between pi and minus pi, so that comes from this inequality here. So the conclusion is that xi minus 1 minus xi is not 0, and it's not big enough to be a multiple of pi. So since pi is a factor of this first of the left hand side, it means it has to particularly divide this one. So we get that pi divides this sum. Okay, and now this sum here lies strictly between 0 and 2 pi. So to see that, we use the less strict inequality, so the more precise inequality up here. When we add that, we see that this is indeed works out like this. So since pi divides it and it lies between 0 and 2 pi, only multiple that satisfies that with pi, so we get that this sum is pi. And this in fact is the third expression here. This third expression can actually be gotten by adding the first 2 and dividing by 2. So to get the other 2, you just need to get we get what will be equivalent to like the difference. So that follows from the same equation, this difference here. We see that we can now cancel out pi, and we left with the pi minus 1 minus pi plus 1 on one hand and xi minus 1 minus xi on the other hand. So if we pair these two together by adding them or by subtracting them, we get the two required results. So if we add them, xi cancels out, subtract xi minus 1 cancels out. Okay, so we'll be making use of the equations that involve these four expressions for the most part. Okay, so now we are ready to start creating the building blocks. So first of all, we have to get the definition of a very crucial piece, which is what I would call a super prime. So we'll call pi in a particular circle a super prime if it is as big as this, so it's greater than pi minus 1 plus pi plus 1 plus 1. That's when you add the neighboring primes plus 1 is still greater than that. So for such prime, we call it super prime, and this has a very central role, which you will see especially in the next lemma. So lemma 2 now says that if P is a super prime of C, then the circle that we get by removing Pi is also actually a circle. So that's what we're discussing up here. So for example, when we remove 31, do we get a circle? Like, is there going to be a connection between 7 and 11? For example, if we remove 5, is there going to be a connection between 11 and 29? So as long as once we have a super prime, we can actually safely remove that prime and we indeed have a connection. So we only need to show that the connection exists, but we can also more precisely get exactly what the connection is. So here we will show that we have such an x. So our goal is to show a connection now between pi minus 1 and pi plus 1. Let's just call that connection x, right? So of course x is positive. This is what we want to show, that we have something like this. Alright, so now we start with the condition given for pi being a super prime, and once the super prime clearly is going to be greater than both neighbors, so now we can use lemma 1. So from lemma 1 we have this as the first equality, and then combining this with the given inequality right here, we get this, and simplifying we see that xi minus 1 has to be greater than pi minus 1. Okay, and so now because of that we can set x to be xi minus 1 minus pi minus 1, since that difference will be positive, and in fact it's going to be equal to xi minus pi plus 1, which we can get by looking back to this difference. So just rearranging some of these terms, we get back what we talked about here. Alright, so now we see that what we just need to do is we claim that this x is the x we're looking at, so we just need to show that if we start with this x squared plus x plus k, we actually do get the product of those two neighbors. So this is just a simple algebra expansion. We plug in this expression, and when we expand we see that we can collect the terms with the xi minus 1 on one hand together with k, and then we also have those that have pi minus 1 somewhere. We can factorize them. So once we've done this, we see that this just is a connection between pi minus 1 and pi, and on the other hand from lemma 1, that's the equation we have right here, by rearranging some terms we get that is equal to pi plus 1 minus pi, and simplifying we get the required result. Okay, so speeding things up, we also have that we can write pi in terms of this new value and the other primes. So just come back here, make xi minus 1 and xi the subject, and using lemma 1 we know we can write pi this way as this is greater than both neighbors, and then we simplify and get this. So this is important because it's going to give us a way of relating to decode what the necessary pi would be if we only had like a smaller circle where we already removed pi. So that's going to be the focus of the next lemma. So in this first lemma we say, okay, we have a super prime, we can remove it to get a smaller circle. So now if we had that same smaller circle, can we actually, when can we, like, we already have a circle like this, when can we be sure that we can create a super prime, and what is it going to look like, right? So we see that once we can create a super prime from a bigger circle from a smaller circle by using lemma 2, we can come back to the same circle, and then pi will have to satisfy this. So meaning that we can't just build starting from pi minus 1 and pi plus 1. We can't just build any random prime. It has to specifically be a prime that satisfies this equation. So the lemma goes like this: if we have like a smaller circle that's missing our potential pi, where there is a connection between all this, so that's why we have a circle. So for now, the connection between the other ones, we use the same alphabet we used before, but the connection between pi minus 1 and pi plus 1, we just simply call it x. Okay, so suppose we already have like this setup. We want to see, can we get some pi? Clearly, if we can get some pi, it has to be of this form. So now, assuming we do place such a pi, can we get a full circle? Right, so that means we have like we have a circle that already has up to pi minus 1 on one end, up to pi plus 1 on the end. We also have the connection here. So we want to see what we can place up here. So from once we can do this from lemma 2, we already said that it has satisfied this equation. So now the issue is, does this actually create a circle? Because for each circle we don't just need the primes, we need the connection. So we need this connection. So that's going to be what we actually need to show, and when we can do that. Okay, so if C is like this, where we place pi exactly at this position of interest, is a well-defined circle with pi, of course, having to satisfy this, and clearly it's going to be a super prime based on this expression. So this is only going to be possible when this expression is prime. So if we have a smaller circle and we check this expression and it's prime, then we can set that prime to be our pi, and we claim that we do have a bigger circle. Of course, if it's not prime, then there's nothing to talk about. So the going one direction is the part where suppose it's not prime. So that's just from lemma 2. For it to be prime, for us to have this circle, that expression just has to be prime. Now going backwards, if it's prime, does that mean we can actually complete the circle? So based on what we had in lemma 2, we can actually deduce what the new connections xi minus 1 and xi should be based on what we did up here. So right here, so just reversing that, we know what it has to be. We just need to check that it actually does create a connection. So we let xi minus 1 be this and xi plus 1 be this, and then we just need to check that there's a connection between pi minus 1 and pi. So take the product. Now pi is necessarily has to be given by this equation right here, and plugging that and expanding, we see that we get pi minus 1 squared and so on. Now pi minus 1 times pi plus 1 already has this is already a connection through x, so we can replace that by this expression. And from this we can now see that we have some kind of squares going on, like pi minus 1 squared, x squared, 2x pi minus 1. So we can factorize that into a perfect square, and we are left with this. So plugging what we had as the xi minus 1, we can just make that substitution, and we indeed get the connection we desire. The other is going to just work the same because there's a symmetry going on about pi minus 1 and pi plus 1. So we can just do this exactly the same the same expansions and collection and factorization, get the same result. So that brings us to the next one, which is that now we know that we can decompose a bigger circle into a smaller one through super primes, and with the right condition we can build back to a bigger circle, creating a super prime, right? So now what we're going to show is that once we have a circle, there's only one way to actually build a particular prime out of it. So we're going to assume now for lemma 4 that pi is a super prime of C. So that is a super prime in some big circle. So I want to show that there's going to be unique primes where they are distinct primes, such that we can draw a connection between P and Q, and also Pi is equal to P plus Q plus 2x plus 1, where x is that connection. So this is exactly the equation we're dealing with in Lemma 3. So what this means is that if we have P and Q in some circle, it doesn't have to be C, it doesn't have to be a smaller version of C. In just any circle, so long as we have the same K, right? Once we have P and Q having a connection, so maybe they are adjacent, we can, so this condition here just simply means that Pi potentially can be created from P and Q. So we are saying that there's going to have to be a unique value, a unique pair P and Q, where we can have this. So we cannot create P from any other pair whatsoever, no matter where, right? So clearly they exist P and Q that satisfies this, because Pi is a super prime. So clearly Pi minus 1 and Pi plus 1 would be such a P and Q. So the existence is not the problem. The concentration here is that we can only do this one way, which is the uniqueness. So we always keep in mind that it's always possible to get P and Q. So we use that to our advantage at some point. So I want to show uniqueness. Now we have, based on the conditions of P and Q, so we have two equations. So two equations, and we have x. So we can sort of eliminate x by taking P plus Q minus Pi, which will be minus 2x minus 1. We square that, and we see that we can actually efficiently eliminate x this way. Now once we expand, it's interesting that we actually get a very symmetric figure here. So if we expand this, we're going to get everything except this will be plus, and then once you subtract 4pq, you get this expression. So from this now, we can actually focus on Pi as a central figure and try to see how we can potentially solve for P and Q. So this is quadratic P and Q, but we can complete the square quite easily for P and Q this way. So we can look at the difference squared minus this, and then the sum. So the idea here is that we want to show that we can get the difference in a unique way, and also the sum in a unique way, and then from that we can get P and Q. Because once we have the sum and difference of two numbers, we can solve a simultaneous equation to get the original two numbers. So if we can get P minus Q uniquely and P plus Q uniquely, we're done. So first of all, we pay attention to the fact that P minus Q satisfies certain properties which we'll use. So first of all, if you take mode Pi of this equation, this is going to disappear, this will disappear, and get this simple nice quadratic congruency. Also, since we have that Pi is equal to P plus Q plus 2x plus 1, x is positive, it automatically means that Pi is greater than both P and Q because they are positive. So their difference has to also be less than Pi. Also, we can't have difference being 0, because that would mean P and Q are the same. So that is comes in play here, since we have that P and Q have to be distinct. And of course, logically, we don't want P and Q to be the same, because it's like trying to create P out of just a single prime. So we do need two primes to create a new prime. Okay, so finally we have P minus Q is going to be even, and that comes from the fact that since we have P Q is x squared plus x plus k, and k is odd, so it means that we have that x squared plus x will have this, x squared and x will have the same parity. So this is even, this part is odd, so this will be odd, and so we can only have P and Q being odd numbers, and their difference will certainly be even. Okay, so we must have this, any P and Q that satisfies the initial conditions. So this means that t squared congruent to 1 minus 4k, now focusing on this first part, has at least one solution. That's minus 1 minus 4k is a quadratic residue. And why we can say this, because we already know an example of a p and q that exists, so that's already a solution. And in fact, from this second part, we know that p and q is not a multiple of pi, so in fact this cannot be congruent to 0. And once we have that it's not congruent to 0, there are always going to be two solutions in the range 0 and pi. So that's because once we pick one solution, then since we have a quadratic congruency, we can factorize to get out a second solution, which will always be pi minus t. So now the interesting part here is that once we have pi being an odd prime, then if t is not even, pi minus t will have to be even. In fact, exactly one of them will be even. So what does this mean? It means that even though we have two solutions, once we restrict and add in this third sort of condition, we're going to get a unique solution. So putting out more clearly here, if you have t satisfying this system, we have congruency in the range as even, then you have a unique value, and this value depends only on pi. We know it exists, but it must depend strictly on pi. So we can only solve this with pi and make these other decisions. So keep in mind that t naught being unique depends strictly on pi. It has not to do with p and q. Okay, so now we have that p minus q, the absolute value of that, satisfies exactly the axioms for t. And we know this has only one solution, t naught. So p minus q, the absolute value of that, has to be exactly t naught. So don't really get a choice for that. And plugging into the symmetry equation we got before, we see now that we can try to make p plus q like subject. So the difference is fixed, and that somehow fixes the sum as well. So before we do that, we have to just observe that 4 and pi both devise t naught squared plus this, and by Chinese method theorem we can place them together. So how do we know pi divises? Simple, just take mode pi, and we are back to this congruency. And also on the other hand, if you look at t naught being even, t naught squared would be divisible by 4. Okay, and then clearly 4 divides 4k, and p squared minus 1 by difference of 2 squared, the product of two even numbers, so it's also a multiple of 4. So this is a multiple of 4. Since pi is even, is odd, we can multiply these two to get this result. So what this means is that p plus q will have to actually be an even number. Okay, so from this we can now get p and q, because we know their difference, we know their sum. Of course we don't know p minus q is t naught, but we know it's going to be plus or minus t naught, depending on whether it's positive or negative. So that's not really important. So from the sum and the difference, by making p plus q subject here, we can get the exact expression for p and q, and this depends entirely on pi, since t naught depends on pi. Now we have only two values, one will be p, one will be q, and it doesn't really matter which one we pick as p and q. We just know that those are the two neighbors of pi. They have to be the two neighbors of pi as a pair. Okay, so now this takes us to the next part. So we already know that we can decompose and we can build back, and in fact we can build back in a unique way. But this all depends on the fact that we start with a super prime. So what happens in the case where we don't have a super prime? So we look at where we don't have a super prime, and for this we assume n is greater than or equal to 4, but as we'll see later, n equal to 3 is actually going to be trivial. So when n is greater than or equal to 4 and c has a super prime, it turns out is a very unique setup we must have. In fact, n must be 4, k has to be product of two opposite primes in that circle, and the other two primes will have to be twin primes that satisfy this respective conditions. Okay, so To do this, we know there are no super primes, so we're going to start with a prime that is as big as possible. So ideally we'll pick P2, just the biggest among all the primes. We'll arrange the circle by rotation or reflection, either way. We will arrange it in a way that P2 becomes the maximum, right? So in particular, we know P2 is already bigger than the neighbors, so we can use Lemma 1 efficiently. Also, we know P2 is not a super prime, so it satisfies the reverse condition for super primes. So with these two in place, we can use Lemma 1, which gives that a connection between P2 and P3, which is x2, satisfies this P2 plus P3 minus P1. And from this inequality, we get this, and simplifies to x2 less than or equal to P3. Okay. So, of course, in a similar way, x1 will be less than or equal to P1. Now, if we look at, so we have this P2, the maximum. Of course, we have two neighbors. There's nothing special about any of the neighbors, so we can just go beyond any particular one. Let's say P4. We see that P2 is also greater than P4. So, by looking at their connection, which is x2 squared, x2 plus k, and x3 squared, x3 plus k, we see that x2 has to be greater than x3 because they're dealing with positive numbers, and that gives us this lineup. So this is a similar situation to what we had when proving Lemma 1. So in particular, this means that P3 cannot divide this difference, because first of all, the difference is positive here, and is also going to be less than P3 because x3 is positive. And from that, we can do the same thing we did before by taking difference of these two expressions and we factorize. So we get this similar to what we did with x and y at the start. So P3 is a factor, but it doesn't divide this, so it divides the other part. So far so good, and we have this. So similar to what we did in Lemma 1, we're going to have this inequality. So there's a difference which I think plays an important role here, which is that this inequality here is not strict, unlike what we had before. So the conclusion is going to be a bit different from what we're expecting. So first of all, it means that as a multiple of P, you have two options. It could be P3, it could be 2P3. First of all, we show that it cannot actually be P3, so it has to be the other option we never consider. Suppose it's P3, then everything is going to follow similar to Lemma 1, so we can plug that back here. We can now get the difference to be x2 minus x3 is P2 minus P4. From this, we can solve this simultaneously by adding both equations, and we get this, which is very familiar because this is actually similar to what we had in Lemma 1, with just one difference, which is P4 and P1. So this means that P4 has to be equal to P1, and if you look at it in terms of our diagram, it means that after P3, which is supposed to be P4, we get back to P1. So this means the cycle has to be of length 3, and we're looking at the case where n starts from 4, so this is a contradiction. So this means that we could only have the other possibility that this sum is equal to 2P3. Okay, and with this our initial lineup, we know that this has to be where equality holds. That's for all this inequality we got before. So this led to this, right? So now we have equality. That forces equality to hold as well in the original inequality. So this means that the particular x2 have to be as big as possible. Same with x3. So x2 must be P3, x3 must be 1 less than that. And once we have this, we can go once again back to this difference. Go back to this difference. We now know x2 minus x3 will be 1 because they are both, this is P3, this is P3 minus 1. This is already 2P3. And once we cancel P3 out, we see that P2 and P4 will have to be twin primes. That's the difference is 2. Okay. So in the way we did this, we see that we can also do this for P4, for going backwards. Guys, here we got P4, but we could go in this direction based on symmetry, and of course, since we have n elements, this will have to be Pn. So exactly what happened with P4, we get very similar result with Pn. And now we got that P2 and P4 are P3 primes, so that means Pn and P2 in particular will be P3 primes, and in fact Pn will have to be P4. So this is a complete diagram of what we get. So the way we got x2, the connection between P2 and P3 to be P3, and this will be P3 minus 1, and get connection between P1 and P2 to be P1 and P1 minus 1, or P1 and Pn. Alright, so doing this in a similar way for Pn, we get that Pn P2 minus Pn is also 2, and connecting these two together, Pn is 4, and then that means in fact this are the same primes, so we must have n is 4. So we already show n is 4, so we need to prove the remaining parts. So from lemma 1, we already know P2 can be written as the sum of those two connections plus 1, and we already know what the connections are. So in fact this is P1 plus P3 plus 1. So this means that equality actually holds for this inequality right here. So it's as extreme as it gets. Okay, so this also means that since we know P4 is 2 less than P2, we can get the expression for both P2 and P4 at the same time. So this shows the connection between P2 and P4, and we also know their connections in terms of x. So finally we just need to know about k, and we see that since x1 is P1, we can just plug that here and see as x1 is connection between P1 and P2, we get this, and we now know the expression for P2 in terms of P1 and P3, so we can in fact get k in terms of P1 and P3. Turns out it's just the product. So we now have all the elements we need that we required for lemma 5. So we have n is 4, we have the highest prime is this, we have P4 to be twin prime with P2, and k is product of the initial opposite primes. So we are going to now explain why we would want to look at P5, like what does this actually do for us. So the idea here is that we have let's say we have a circle of interest, right? So ideally this circle is going to have some super primes. If it has, let's say, super prime pi, we can remove that super prime to get a smaller circle using lemma 2. We can keep doing this so long as there are super primes. We can keep doing this until we get the shortest circle where we can't do this anymore, meaning that either n is no longer equal to 3, so that means we have 2 elements, or we have n equal to 3 but no super prime. And if n is equal to 2 or n equal to 3 and so on, it's going to be trivial because it doesn't matter if you have, let's say, 3 primes for instance, P2, P3, it doesn't really matter the arrangement. This is just going to be, whatever permutation we do, this is just going to still represent the same connection. We must have all 3 connections, so some x3 here, x1, x2. So there's only one way to arrange this because each of these x are already unique and so on. So there's just only one way to arrange this. You can draw it in different ways, but once you ignore rotations and reflections, then you have a unique presentation. Clearly the same applies for 2 and 1. And so that's why we are interested in starting from 4 and beyond. So this C prime, if it's either of these, then obviously we already have a unique way we can express those remaining primes. If on the other hand C prime has at least 4 elements, then from lemma 5 now we know that it has to be that n must be 4, and not just that, that k must have been, no, k is fixed, but that k must have been the product of 2 primes in C prime. So we don't get to actually choose which primes will have to appear in C prime, so long as we have this scenario. And now P1 and P3 can never have connection, because if we try to make a connection, you see that this is already P1, P3, so we have to have that this will be 0, so x is either 0 or minus 1, so it's not positive. So in fact, there's no connection between P1 and P3. So among those 4 elements, we cannot have P1 and P3 side by side. So the neighbors of P1 have to be the other 2. We can place them in any way, and then we see that P3 have to just be the last one. So there's only one way to actually just go about this, so long as we assume reflections and rotations give the same figure. Okay, so so this means that once we continue doing this until we don't have any super prime anymore, that we already have a unique setup. So now what we do is we try to see that if we want to get back to C itself, we have to start placing back all the primes we have to place back all the primes we removed. So let's say we could end up with a different circle where it's a permutation of the circle C, right? That's a different circle. Then in the same way, we can also keep removing the super primes, and we end up with the same scenario. Because we have to get back to where we don't have super primes, and then we still get whatever conclusions we made here before we get the same conclusion. So this means that actually, since C, the new C can also get back to this C prime, going backwards, meaning there's a way we can actually construct C C dash by starting with C prime. So this means that we are claiming we have 2 ways of getting a circle having all the primes in C, starting from C prime. Now each prime we had in C will have to come in at some point, and from what we had in Lemma 4, we see that every prime coming in will have to be like a super prime of the new circle we get, and it can only come from 2 specific primes once we have the P in mind, right? So this means that given any Pi, once we want to add it at any point in either of these extensions, that Pi, that we must have both P and Q present, and Pi will have to end up in their middle. So that makes them the same in that sense, and we can keep doing that until we put all the primes, and then we see that we just get exactly the same figure, because they can only come from exactly the same pairs of primes each time. It doesn't really matter the order which we decide to place them. Whenever we place them, they must end up looking exactly the same, and so we end up getting the same circles. Okay, so this brings us to the end, and before I conclude, just take a quick look at this example I gave at the start. So this example actually starts with if a C prime where we had n equal to 4 and k35 means that we have to have 5 and 7 as the 2 primes. So this is like a P1, P3, and we can actually just create more examples like this from n equal to 4 by starting with, let's say, 2 primes, let's say 13 and 11. We need P1 plus P3 to be the number in between as 12, so we get 5 and 7 as the correct ones. So we have an initial setup as something like 11, maybe 13, 7, 5, 5. So this is like the initial setup primes. And also from Lemma 5, we know the connection here will be 5, 7, 6, minus 1, 4, 6. So this is how we can construct beyond this. We have to compute the expression Pi minus 1, Pi plus 1 plus 2xi each time. If it's prime, means there's a potential way we can build up. So for instance, we can actually, to compute it, so that we can actually create the prime here and it has to be 31. We can also create the prime here, it has to be 29 and so on. So now if we already had this setup with these 6 primes, 31, 11, 5, 29, 13 and 7, and we want to check if there's another circle that could have this. So first of all, we see that 31 is a super prime, 29 is also a super prime, so we can remove these two at any point in time. Once we do that, we always come back to this original setup, and we cannot remove any other primes outside of that. And so once we get to this original setup, we see that at some point we have to add 29, but 29 can only come from 13 and 5, meaning that before we add 29 we must have 13 and 5, and once we have 13 and 5, 29 must come in exactly this way. So that's just what I was explaining. So this means that we must have 13 and 5. If we already do, fine. If we don't, we have to now add those ones first. So if we don't have, if we imagine we didn't have 13, we have to, that means there must be a way to add 13, and we have to add it first, and also it will also be added in a unique way, inductively like that. So once we have 13, we also have 5 on the other hand. 29 must come into the middle, the same with 31 and so on. So we do that until we end up getting just the same circle again, as long as we still want the same set of times. Okay, so that'll bring us to the end of this. I hope you enjoyed. You can drop your like and you can subscribe. Thank you for watching. See you in the next one. Bye.